Okay, the quiz is just basically most of it is what you would have done in analyzing the lab. Okay. And I got labs and homework. I haven't checked against the roster to see who did because they came in at different times. I just looked at them. The homework looked pretty good. Wasn't without errors in some cases, but you know, the process was valid. And maybe some errors and details that I'll address later. I will say, I'm going to give you notes in your homework. I'm going to have a PDF. Do a PDF, email me. If you got a smartphone, it's just download a scanner app. It'll make you PDF. Then I can work. I get JPEGs, I can't do a thing with them except look at them. Okay. Yeah, there's some things, you know, people are on the whole using units. Sometimes they didn't use them correctly. Sometimes they have one unit in this step, and then they didn't bother simplifying the unit. They just wrote down the unit they thought should be. So they got V squared was in meters per second. You know, V squared is in the square of meters per second, right? Because V is in meters per second. And then they took the square root of that and still got meters per second. Square root of meters per second is not meters per second. You know, that's one that I just remember kind of stood out. The problem's done well. It's just, there was
This is
a scary carelessness with the units. Okay. And you really got to be a little better with that, using the units. Okay, well, anyhow. Okay, well, first of all, what's omega of 0? You got to find omega of t. There it is. It's easy. I didn't put a t term in the end because it makes the algebra a little easier. Okay. So if I want to solve for omega equals 0, well, I just use intermediate algebra, which not everybody did. Okay. So you want to kind of refresh your intermediate algebra a little bit. I think you need that from engineering courses too. Okay, there's your omega. Okay, so omega equals 0 is okay. What kind of an equation is this? It's a quadratic equation. It's an ax squared, at squared plus bt plus c equals 0, or c is 0. Well, when c is 0, you can solve this by factoring. You just factor this and you say, okay, that's t times 0.0006 t minus 0.01 equals 0. So now there are two solutions.
All the ingredient labels.
And if that's not familiar to you, get familiar with it, because that's how you solve polynomial equations and all other kinds of equations that are equal to 0. You use the 0 property of multiplication. If this times this is 0, this has to be 0, or this has to be 0. So you factor and use the 0 property of multiplication. That you're going to run into that. You don't always let the software do it. If you don't know what's going on with that, then you don't have a handle on the situation. You let AI do it for you, well, you don't have a handle on anything. Okay. Okay, so anyhow, I don't have to solve this for you. All I've got to do is move the decimal over a couple of places. That's supposed to be a brace. 0, comma.
Another product. All right, well, let's talk about
I'm going blind. I'm getting too many decimal places in this thing. I mean, you get, divide 1 by 6, you get 0.162 0.167, basically. I think you get t equals 167. 167, yeah, that's gonna give you 0.01. Okay. Somehow my brain just stopped functioning there for a minute. But came up a few hours short of sleep last night, but I feel pretty good. Feel good when you aren't very good. Okay, so anyhow, so it's like if t's in seconds, 167 seconds, a little over 2 minutes, close to 3 minutes, which is kind of consistent with the theta functions you got. I mean, the numbers are different, but it's should be in familiar ground if you've done the work yourself. Okay, if you've solved the equations, which most of you did, because I saw the write-ups you gave me. And as I say, those write-ups on the whole look pretty good. Okay. I think most people were getting the same things. I will mention on the write-ups of the lab, I am going to ask you for a summary of your results. Okay. What questions were asked? What are the answers? You showed me. So, okay. I want to see a summary of results. And generally in the lab, you want to do that. And then you show the details of the calculations separately. So I can look through the details, but sometimes I want to compare yours with somebody else's, and I don't want to look through pages of details to find the results, especially when I'm getting them at different times. Okay. If I got them all at the same time, I go through them all at once, then I'd remember what the results and whether your results were killed over somebody else's. Okay. And see what the variation in the results is, because everybody is going to be sitting at a little different point. There's going to be a little difference in that. Probably almost everybody missed one place or another. Okay, plenty of opportunity to do that. So we want to see from the results how reliable this 5-part instrument is. Okay. Well, all that's involved with this problem. Let's continue. Something moved. Thought I killed everything over there. Okay. So when is omega equal to 0? There's my solution. And we actually disregard the solution. T equals 0. Because the velocity is 0 right up to t equals 0. But if t equals 0 is the instant at which I release this thing, then the velocity is not 0. So sometimes your equations will give you a solution that doesn't fit the physics, doesn't fit the situation. Okay. All right. Alpha of 0. Well, To get alpha of 0, we better get alpha of t. And alpha of t is
Other. Why?
0.00012t minus 0.01. So that alpha of 0 and actually, if this is what we did, t is not measured in seconds, it's measured in ticks. Where a tick is a little less than a second. Maybe it's a little more than a second. Doesn't matter, it's a tick. We want to, so we're doing revolutions per tick. If we start doing physics with this stuff, start doing the dynamics, then we want to go to SI units or some persistent set of familiar units, and we're going to be using radians rather than revolutions. Right now, revolutions per tick is just fine. It's real easy. Replace revolution by 2 pi radians. And if we know how many seconds there were in a tick, and we've got videos of the tick, start the video, count the ticks for 60 seconds and see how many there were, even 30 seconds, 20 seconds. Okay? Okay, so anyhow, alpha of 0 is negative 0.01, corresponding to 0.01 revolution, not per tick, but per tick squared. Okay? I never did calculate omega of 0. I just went directly to this just because of some stuff I saw. Okay, so anyhow, there's alpha of 0. That means we're losing 1 revolution per tick every 100 seconds. Okay? Get omega of 0. Okay, got a problem there because I didn't put a t term in. We're getting omega of 0 equals 0. I left the t term off to make the arithmetic easy. Wasn't thinking clearly. Okay. So I'm going to have to modify this, and then I'll have to modify this solution. So I'll just kind of leave that there, but I'll start doing some stuff over here. Make sure camera is far enough to the left. Okay. Something's wrong here. Some stuff in the board, whatever. I don't know what it is.
Somebody. Another art here stating exactly the building or that. A letter. solar exposure. With the sea. Mineral. Wild spring green.
Yeah, okay. If I put this 0.2 T in here, omega of T is then going to be plus 0.2. Same thing I had before. Then if we want to know when T equals 0, or omega equals 0, then we don't even try to factor this. It'd be crazy just from real world data. Okay, the chances that you're going to run into something you can factor are pretty minuscule. And you get T equals 0.1 plus or minus the square root of minus 4 times this times this. And I'm just using the quadratic formula, and I'm not going to tell you the quadratic formula. You just know how to use that. If you don't, but I'll do the arithmetic in my head here so I can really screw it up. So that would give me a 1, 2 here, and then it's going to be a 4, 8. And that's going to be over 2. And that's going to be 0.00052. And the square root of that will be gotta be careful. Better to write this out than do it in my head. I'm gonna do it in my head anyway. That's gonna be 0.00052. Yeah, might be 0.025. No, could be 0.25. It'd be 625. That's too high. 0.022. Over. Okay, the plus is going to give me 0.032. And
So these.
7. Or negative, which we disregard. Because negative time has no meaning here. Because we didn't start the thing until T equals 0, or at least it might have been moving before. So sometimes we wouldn't want to disregard that. But if the acceleration's uniform, it turns out we have to anyway. And won't go into detail. You get something absurd if you use the negative. You couldn't even interpret physically in terms of the system as we observed it. Okay, well, that's a little more detail than I wanted to go into on this, but that does change. Okay, then what is alpha of 0? Well, alpha is still going to be what it was because that 0.2t just becomes, did I ever write the equation out? Anyhow, it becomes 0.01t. We take the derivative of that. We get the 0.01, the derivative of the 0.2 though goes away, right? So by the time you get to the second derivative, you don't have it. So this is valid. Okay, so our initial acceleration is negative 0.01 revolution per tick squared. Our initial velocity is where did I write it down? I mean, there it is. It's 0.2 radians per second. Anyhow, if t is 0, you're going to get the 0.2, right? Or 0.2 radians per tick. So we can summarize if I did my arithmetic right. Okay. Now, what's the next question? When is omega equal to 0? Well, we got that. Alpha is 0, we got that. It's negative 0.01 revolutions per tick squared. Now, average value of alpha is what? Well, we can do it turns out that the alpha function, which I've got down here, is this. This is a linear function. When t equals 0, it's equal to negative 0.01. And this isn't going to be consistent.
I have you do what the binomial nomenclature with binomial. Yeah, binomial is referring to them having two names.
So we could have an error here. I don't want to spend too much time on errors because I'm doing this in my head. Probably should have worked it out earlier, but I didn't. if I set this equal to 0, I get 0.01 over 12. But alpha has to equal 0 just before the thing comes to rest at 267 seconds. Well, if I put 267 into here, I don't get 0.01. Okay. Get like 0.03. So something's inconsistent. So we'll stop there for the moment, and then I'll work this out and talk about it again next time. But anyhow, thing's going to have a straight line graph. So you are going to be able to get the average alpha. But the other thing is that ought to be equal to the initial value of alpha averaged with the final value if the acceleration is uniform.
You might say that's proving. Vegetating. So, yeah, what's it called? Angel, Dark, what is it?
And the average alpha would be the initial plus the final acceleration. Actually, I'm getting a final acceleration that's positive. So I'm just going to say is itself. And I apologize for getting messed up with these calculations. I tried to make them simple, but I overdid that. I had to do some more complicated calculations and imagine I messed anything up, but apparently did. Okay. So we'll leave it at that. But again, that should give you some more insight having done the analysis. The lab. We can measure the average acceleration for the first 20 ticks. You get a pretty good idea what the initial acceleration would have been. And we can measure it for the last 20 ticks and see where it's going and see if the average of those is equal to the average acceleration. Because we get the average velocity for the first 20 ticks and the average velocity for the last. So we know what the change in velocity is, and we can compare all that. And we can get evidence of the nonlinearity. And I think some of you picked up on that in your lab. But that's one of those things that I don't expect everybody to pick up. So I'll give them a closer reading now that I have them all, so I can make comparisons. Also, your handwriting was pretty good. The PDFs would be better because sometimes your handwriting is pretty light. And it's hard for me to read it in the screen. Okay. So again, learn how to put those things into PDFs. It just comes down to download a scanner app and use it. If that doesn't work for you, let me know. I won't know what to do except download a different app and use it. Or if you have the app, we can look at how it behaves. Okay, well, homework again. I think I got it from almost all of you, maybe from all of you. Again, I'm not checking it off at this point. Partly because it was due last night, I had a lot to do last night, this morning. Like my phone carrier told me, oh, you gotta go fiber optic, and you gotta pay by automatic draft, which is no problem. Okay? And we're gonna try to sell you this internet package. The guy came to the house the next day. And the internet package looked pretty good. So they installed it the following day and disconnected my dang phone. Also, they emailed me a form that was identical to the form I filled out for the guys. Well, I've got to fill this out. They say fill it out. And then my wife did something else. Now we have 3 accounts. And the carrier doesn't know which account is which, and they're all confused. And the people you talk to aren't quite bright enough to get it straight. This is pretty complicated. Okay, even though I'm telling them exactly. So my wife's got serious medical issues. We don't have a phone. I'm not happy. Anyhow, I've had to deal with that. Not an excuse, but it's one of the things that's been going on. So I didn't get to look at everything that I would have liked to, okay? But I did read through all the homework. So I see the patterns, and I don't see anything that really scares me at this point, assuming it's your own work that you're showing me. And everybody made too many mistakes for it to be somebody else's work. They did make many mistakes, but there were some mistakes, okay? So I'm fairly comfortable with everybody that handed in the homework. Okay. Also, as engineers, you're going to have to deal with complicated incompetence, which is one of the reasons I mentioned the thing with my phone. Okay. Oh, yeah, then we got an email saying, you're going to confirm the installation for Wednesday? We said, yeah. And they said, oh, sorry, it's canceled. We don't know. Oh, landline. Okay. I have just one more thing that's relevant to engineering. Clearly, the best physics student I've had in the last decade. It's been a good chunk of a decade since. It doesn't seem like time's gone that quickly. Went to MIT, graduated with honors. Went to work for a company, stayed with them for a while. Decided to get into this really exclusive master's degree program with MIT because being an engineer, he was always getting overruled by managers that didn't know what they were talking about. He'd say, this isn't going to work. Here's the physics why it doesn't work. Here's the math why it doesn't work. Here's another reason it doesn't work. And then he has 3 or 4 other engineers corroborating him. They say, do it anyway. We've got to do something. All right. That's very analogous to what I was just talking about with this company, although I'm dealing with a much lower level of competence when I'm talking on the phone to the people that I have talking on the phone. Okay. And I don't know what it takes to get to somebody. And they did pretty well. They listened to me. We came to an agreement about how to fix this, how to meld the 3 accounts into the one we've had for 100 years. So no stones to throw at them. They have their limits. And so do engineers and engineering managers. My grandson working for Norfolk Naval can't tell me much about what he's working on because he's working on nuclear subs and aircraft carriers. Not on the nuclear part, but on the power system to come off of things. And he says, you get something that you need to do, you know you need to do it today. You just got to go through 3 levels of approval. And one of those levels is somebody who's not on the job until 6 p.m. tonight. You know, be prepared. Okay, back to the physics now. Which time is wasted? It's not a waste, I don't think. I want to deal all with this situation. Watch. I'm starting this from a height of 120 centimeters. Okay, I'm going to toss it up, so it's going to go up in the air exactly 1.3 meters before coming back down. Now, most people can't do that, but I can. Watch 1.3 meters, then come back down. Okay, you can actually time those events and see if it really went up 1.3 meters before it came back down. And there was a problem in your homework that was equivalent to doing exactly that. And everybody seemed to get, you know, how high does it go off the diving? First, one thing about solving that problem, I want to know how long it takes to get to the floor. There are a couple of ways I can do it, depending what information I have. And the information I had, my hand is calibrated very well so that I could get the exact velocity that I needed. And the camera's out of focus. More technology. Okay. Now to go up 1.2 meters. Okay. How do you solve how long it takes to go up 1.2 meters? Well, just using the equations because it's a little tough to solve in your head unless you're really used to the equations, right? I'll say delta S because it's not really an X. X is that way. This is could be a delta Y, but I'm just going to use delta S as a generic displacement. Okay, it's 1.2 meters. Acceleration, I would like to use 9.8. I use 10 meters per second squared, then do a 2% correction. Okay. And you can do that on tests. You can just do 10 meters per second, unless I say other 10 meters per second squared, unless I say otherwise. Just makes it easier to calculate. There's no point in using 9.8 when it's really probably, you know, at this altitude, maybe it's 9.793. So it's not, 9.8 is not totally accurate. And the actual acceleration of gravity depends on where you are on the surface of the Earth. Hopefully not too far under the surface. Okay, gets hot down there. Okay, so we have this. And let's say we're trying to find the time in VF equals 0, right? Now, which of the four equations of motion are we going to use? Well, we're going to use the information to do this. This is 0. No, 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 that's not going to help because we need to find V naught, right? So we have V naught. Wait a minute. Never mind, we can use this. Okay, V naught is 0, so that and I know what I'm talking about here. Yeah, all right, what I'm really wanting to show you is you don't need to do certain things. Okay. But V naught. I'm trying to solve for V naught. So P naught T plus 1/2 AT squared equals 0. So that V naught's negative 1/2 AT squared divided by T. Now, the problem is what we said earlier, you don't know what T was either. So what are you going to do? You're going to say we know delta S A VF. We have the equations. I'm using T and delta T kind of interchangeably.
Vì khán giả lãnh vào phía nước ép. Em làm nào chế, em làm
I'm blaming this on bright speed, but that's not a valid equation. So eventually I'm going to learn to do a little physics here. Okay.
So, at the
We have this equation. Unfortunately, we don't know V naught or T. So it won't work any more than the other one did. We have
big
this.
three,
We have VF equals V naught plus AT. And we have VF squared equals V naught squared plus 2A delta S. Which of these equations checks all the boxes for delta S, A, and VF, which are the three that we know? And it's going to be this last one. Okay, so we know VF, we know A, and we know delta S. So that solution of V naught squared equals negative 2A delta S is V naught equals plus or minus the square root of negative 2A delta S. Now, we're taking the square root of a negative. Kind of looks that way when you look at that equation. But A is itself negative. So when we plug in the numbers, we get this. It might be a little hard to read, but you know what the numbers are going to be. We're going to have meters per second squared times meters. Which is going to be plus or minus the square root of 24 meters squared per second squared. And that's 4.9 meters per second. On at least one paper, I saw meters per second squared times meters equal to meters per second. And then the square root of that was again meters per second. That's what I mentioned earlier. It was, I think, in the use of that equation. Okay, now. Yep, that works. If you follow a meter, you end up at about 4 meters per second. So that's in the right ballpark. Can I see all that? See it, 4.9. Yeah, it's just basically barely there. Okay. Now my question is, toss this up, so it goes up exactly 1.2 meters, again, comes back down. Okay, a couple of questions you can ask. When does it come back to the original point? Or how long is it in the air? That was a diving board problem. And most people said, okay, well, it takes this long to go up and down. And then if we start up here and follow all the way, it takes that one. We add that to how long it took to get up. Well, which is valid, but a little more complicated than you need if you know enough information. Now, given the information you had, it was a plausible way to solve the problem. I want you to be aware that and it's supposed to be plus or minus. And now we choose the plus because it ain't going to go up unless this is plus. So we disregard the minus because it's not, it can't correspond to the physical situation. Okay. Okay, so V naught equals, I'm just going to use 5 meters per second. And actually, if I'd used 9.8 instead of 10, it might have come out 4.8. I don't know. But anyhow, V naught is 5 meters per second. I said that I was releasing it from 120 centimeters above the floor. That makes sense? So my displacement from here to the floor is negative 120 meters. The initial velocity is 5 meters per second upward. I can solve that all with one equation. Because acceleration, as before, approximately negative 10 meters per second squared. And again, if you want more precision, use 9.8. If you want even more precision, figure out what the acceleration is right there. Okay. Sometimes you do need to know a couple of decimal places in your answer. Okay. Stop that. So again, we know these 3 things. We know V naught, A, and delta S. So we can find VF. Okay. Well, if we do that, V naught squared is going to be about actually 24 meters squared per second squared. Delta S is negative 120 centimeters, twice that. So that's going to be negative 2.4 meters squared per second squared. Well, I better put it in just so we can see the units. So V naught squared is going to be I'm not being real careful with my substitution because that one's obvious. We're squaring 5 meters per second, right? And then we add 2 times In the 120 centimeters, that's a negative 1.2 meters. Is negative 120 centimeters is negative 1.2 meters. So when I multiply this out, I get 12 times 2, 24. And it's meters squared per second squared, because when I multiply meters per second squared by meters, I get meters squared per second squared, and I'd better get meters squared per second squared because I got to add it to meters squared per second squared. And if I'm doing my units and actually doing them and have something wrong in my equation, a lot of times the units are not going to be compatible. And if you're just slapping down whatever units you think ought to be there, you miss an opportunity to make a big mistake. To correct a big mistake, okay? You give yourself more opportunity to make the big mistake. So VF is plus or minus 7 meters per second. We suppress the plus because obviously this thing's going to be moving in the negative direction, which is a direction of acceleration that we chose. We could have chosen upward as positive. Then the delta S would have been negative. And the initial velocity would be negative. Okay. But there it is. And you see, this equation doesn't require us to figure out where we stop. It doesn't require us to do 2 steps. If we simply know that my hand is well calibrated to give something an upward velocity of 5 meters per second, right? Any idiot can do that. Well, believe that or not. And you can check that. It's on the video, and then you have to go on faster. It didn't go high enough. I'd say it went up about 0.8 meters. Okay. So I gotta work on that. All right. Now, reason I kind of stress this problem is anybody out there think they can catch a domino? Throw it back. Ah! Too low. Not bad. It was coming out of the light. I got down there. Always had really good hands.
Wasn't a great throw.
They're wash. Okay. Back here. Okay. So, what I did was I just tossed a domino to one of the class and he caught it like I didn't. So the path of the domino was like so. Okay. Now, here's the point from which I threw it. And here's the point at which it was caught. And here's the peak. Well, we'll call this y equals 0. We'll call this y equals, see, I threw it from about here, and I caught it about here. That's about 50 centimeters. I don't think it's quite a meter. We'll use easy numbers. Okay, here y is 0.5 meters. Now, how high did it go? Let's try this again. Watch it. How much higher is it than my hand? Actually, my hand's almost at the same level. We're gonna show. How high did it go? I toss back. Got to work on that. You make me dive, I'm going to get hurt. Okay, okay, 0.5 meters. Here, how high was it? How much higher than this? Or how much higher than this? This high? This high? Okay, so let's just say it's 1.5 meters. I can easily determine my initial upward velocity. It's exactly the same as this. My delta S is just 1.5 meters. Okay,
Right. Wiley or-
so the V0Y is what? Well, here's the calculation I did for 1.2 meters. If I change that to 1.5, I get square root of 30 meters squared per second squared, which is going to give me about 5.4 or 5.5 meters per second. So we'll just say 5.5 meters per second. And the time interval to go up, well, that's actually pretty easy. 5.5 meters per second and acceleration of -10 meters per second squared. Well, that's number of meters per second. If we change -10 meters per second in that time, it's going to take us a second, right? We change -5.5 meters per second between here and here, it's going to take 0.55 seconds. Now you can work that out if you can use the equations, and everybody seems to be pretty good with the equations. So I don't think you're going to have any trouble working that out. Okay? Now, how far is it from here to the peak? Where do you think we reached the peak? I tossed it from here. Tell me where you think the peak is buried. Tell me when to stop. Okay, well, that's about, so that's 2 meters. And okay, we'll just say that was that was 2 meters. Then we can figure out how much further it went. Okay. The horizontal velocity, air resistance has an insignificant effect on this domino at that speed. At least at the level of anything we can measure. What forces are acting on this thing in the horizontal direction? Air resistance, but that's negligible. What I just said. There are no other forces acting in that direction. Gravity is acting this way. So in that direction, no force. In this direction, plenty of force. Okay, well, that's the basic principle. If your acceleration is 0, your x velocity is constant. Okay, well, that means in the x direction, this thing moved 2 meters in 0.55 seconds. That makes sense?
This thing that popped up in the heart.
So that's horizontal velocity.
Wow.
From release to the peak. That makes sense? And that didn't change after the peak. It stayed the same all the way. So that's approximately equal to 1.8 seconds. Or 1.8, sorry. Okay. Makes sense? Pretty clear?
I thought you were.
So I can determine all this. Now, the key is I was able to determine the time it takes to go up, which is also the time it takes to get from this point to the top point, right? Which is also the time it takes to go 2 meters horizontally. The only thing in common between horizontal and vertical motion is the time. But horizontal and vertical motion over some time interval, okay? Time interval is constant. Well, this is called a projectile problem. You know, that domino is a projectile. Throw a baseball, it's a projectile. Anything that freely falls through the air, even if it's falling upward before it falls downward, is a projectile. And for ideal projectiles, we assume zero acceleration in the x direction, which isn't really true for baseballs if they're hit any distance in front of you. So that gets to be an issue. Or, you know, just try throwing a Nerf ball at somebody. Let it go at 90 miles an hour. See if it hurts them. It's like it hits a wall. Slows down almost instantly and just floats gently the rest of the way. Okay. We could set this up with the equations of motion, obviously. And everything I'm doing here abbreviates an equation of motion. You can see that if you read your book. What you have is vertical motion which simplifies your equation of motion. Common sense is usually, except in one instance, it'll come up in Lab Friday. You'll be able to solve one or the other for the time. So it'll give you one variable that can be used on both sides of the analysis. You've got 4 equations of motion here, 4 equations of motion here. A lot of that you can do by common sense, which is kind of what I've done with most of this. But use the equations. So you get really familiar with them and then think about, well, how could I have done this just from basic principle? I got 0.55 seconds from the basic principle that negative 10 meters per second squared is negative 10 meters per second every second. So if we only change by negative 5.5 meters per second, that's only going to take 0.55 seconds. Okay. The other thing you can then do for that, you can barely do. What angles? Here's my vector V naught. Okay. Using the I and the J vectors that you must be familiar with from other courses.
No.
And from reading over chapters 1 and 2 of the text, I told you to, okay? The trigonometry is pretty simple. What is V naught x? That's the velocity at the initial point in the x direction, and that is what? Well, that's your 1.8 meters per second. And V naught y is 5.5 meters per second K. So your picture of V naught is 1.8 meters per second this way. And 5.5 meters per second this way. I better push it. I think it's still visible, make sure. Okay, so that the result of those two is here. And you know the two components, so you can find the magnitude and the angle. Which I assume you know how to do, and if you don't, look it up. Or email me, I'll give you a couple of formulas. So I've got that next one. Now, if I give you V naught and the angle, you can figure the X and the Y. So you analyze the Y, you can figure out how long it takes to get to the peak, or how long it takes to get up here and back down here, if you know full distance, right? So if you don't even want to know the peak, you know where it starts and where it's going to end. Well, you have those kinds of situations. I'm going to give you a few problems, maybe up to 5 problems. In chapter 3, possibly some of them related to trigonometry, some of them related to the up and down, back and forth motion. But they'll be relatively straightforward problems, so I can give you harder problems in the week. Okay, and that's a pattern I'll usually follow in the channel. Even a few problems to sort things out, get your feet wet. Give you some kind of an introduction. See what you can do. So far, so we're pretty good on the whole. So please keep it up. And I'll look this afternoon when I know what I've said, so that problems I gave you are as closely related to what I said as I wanted to be, which will be pretty close, but not trivial.